Let's go back to angular momentum. Let's look at the angular momentum of this particle. Okay, definition of the angular momentum is that vector is a cross product of the radius vector and the linear momentum vector. We talked about this earlier when we did the particle in a sphere. So the components of your angular momentum are ypz minus zpy. That's the x component. And then the y component is xpz minus zpx. And the z component is xpy minus ypx. Okay? So you can derive this by setting up what this particular determinant. This is what you do when you do a cross product of two vectors. You list, in the first row of your determinant, you write down the unit vectors along the x-axis, the y-axis, and the z-axis. So that's I hat, j hat, and k hat. In the second row, you list the components along the x, y, and z axis of the first vector, in this case your r vector. So what we're saying here is your r vector is x I hat plus y j hat plus z k hat. And in the third row of your determinant, you list the components of your linear momentum vector, your second vector. So this is going to be px I hat plus py j hat plus pz k hat. So those are the two vectors expressed in terms of unit vectors along the x, y, and z axis. So when you do this determinant, you'll find that these are the components of your angular momentum vector. And just like any vector, the sum of the squares of the components will just be equal to the square of the magnitude of the vector. So Lx squared plus Ly squared plus Lz squared equals L squared. All right? So one thing you'll find when you write out these angular momentum vectors and derive the corresponding quantum mechanical operators, you'll find that the L squared operator commutes with each of its components. So the L squared operator commutes with Lx, L squared commutes with Ly, okay, and L squared also commutes with Lz. What does that mean? That means, okay, you can, if L squared and Lx is equal to 0, that means you can simultaneously determine L squared and Lx precisely. All right? Remember our postulate about the uncertainty principle? If the commutator of two operators is 0, so if two operators commute, it's possible to find a common set of eigenfunctions for them. You can determine both of those precisely at the same time. Now, you might be asking, why are we using L squared and not L? Well, it turns out the L operator is not a linear operator. Okay, so we can't be dealing with the L operator. We have to use the L squared operator, which is a linear operator. All right, so anyway, L squared commutes with each of its components, so it's possible to determine the magnitude, the square of the magnitude of your angular momentum, which means you can also determine the magnitude, and any one of the components at the same time. However, the components themselves do not commute. So Lx and Ly hat do not commute. It's equal to I h bar Lz. This is h bar, right? So that's I h bar Lz. And Lx, Ly, Lz is going to be equal to I h bar Lx. And Lz, Lx is going to be equal to I h bar L sub y hat. So the components do not commute with each other. What that means is it's not possible to determine any pair of those components. In other words, of the three components, you can only determine one precisely. So, in other words, what we're saying is quantum mechanics is putting a restriction on what you can know about the angular momentum of your particle. You can determine the magnitude, or the square of the magnitude, and one of the components only, not all three. Because if you can determine all three components, then you would know exactly how your particle is moving. Okay? So significance of that is it's possible to determine L squared okay, and one of the components precisely at the same time. But by doing that, you give up information about the other two components. So, in deriving the spherical harmonics, in solving for the Schrodinger equation and getting the spherical harmonics, what was actually done is it was chosen that L squared, we've chosen to know L squared, simply because of the way your spherical harmonics are defined. The expression for the LZ operator is quite simple, as you've seen earlier. It's just what? H bar over I, d by d phi. So makes it easy to choose that as the component that we want. It's completely arbitrary anyway. Who's to say which one's the z-axis, right? So L squared and LZ, okay, they all commute with each other. So H hat commutes with L squared. H hat commutes with LZ. Actually, it commutes with LX, LY, and LZ also. And so does L squared. And L squared commutes with LZ. So it's possible to precisely determine the energy, which is the eigenvalue of the Hamiltonian, the magnitude of the angular momentum, okay, and one of its components. And if your particle is described by the spherical harmonic that has a well-defined L and M, then we know its energy, very well, but it's very well defined. We know its angular momentum, it's very well defined, and we know the z component of its angular momentum is also very well defined, and they're listed right here. Okay? So, if you were to apply the Hamiltonian operator on your spherical harmonic with quantum numbers L and M, you'll get back a constant times the original function. What is this constant? That's just L times L plus 1 times the rotational constant. That's your energy. Energy is well defined. Okay? We did say the spherical harmonic is the stationary state for your particle in the sphere. If you apply the L squared operator on psi, then you're going to get back this one right here. So these are the allowed values of L squared. L times L plus 1 times h bar squared. Okay? The allowed values of energy are L times L plus 1 times B. And if you apply the L sub z operator on your spherical harmonic, you'll get mh bar times the original function. We've seen this when we talked about the particle on a ring, right? Something similar to this. So LZ is also well defined. Okay? So if your particle is being described by a spherical harmonic, then we know its energy. What's its energy? L times L plus 1 times B. We know what the magnitude of its angular momentum is. It's L times L plus 1 times h bar squared. That's the square of the magnitude. So what's the magnitude? The square root of that. So the magnitude of L itself, square root of L times L plus 1. Let's see. Square root of L times L plus 1 times h bar. Okay? We know the magnitude of your angular momentum vector. And we know what the component of that vector is along the z-axis. It's going to be m h bar. Right? The m quantum number. The m is the m quantum number, not the mass. Okay? So let's apply that. Let's elaborate on that. Let's say your psi corresponds to a spherical harmonic with L equals 2, m equals plus 2. So what's our energy? 6b, right? 2 times 2 plus 1 times b. What's the square of the angular momentum? It's L L plus 1 times h bar squared, right? So it's going to be 6 h bar squared. So what is the magnitude of the angular momentum vector? Square root of 6 h bar. What is the z component of your angular momentum vector? It's going to be 2 h bar. So let's draw that vector. Okay, let's draw your angular momentum vector. So here's your xy plane. Here's your z-axis. Okay, what's the component of that vector, of the angular momentum vector on the z-axis? 2 h bar. So if this is h bar and that's 2 h bar, it's going to be a vector that has a magnitude of how much? Square root of 6 h bar, right? And its component along the z-axis. So if you drop a perpendicular line from the tip of the arrow, remember we represent vectors by arrows, right? So if you drop a perpendicular line from the tip of the arrow to the z-axis, you're going to hit 2 h bar. But that could be, and the magnitude of your vector would be the length of the arrow. So the length of this arrow is going to be square root of 6 h bar, right? But that could be any arrow on what? On a cone, right? That has an angle, has a fixed angle. Let's call this angle, what do you call this? Theta. What's theta? What's this angle that this arrow makes with the z-axis? Pythagorean theorem. Cosine theta, or you can just use cosine theta equals what? Adjacent, which is 2 h bar, over hypotenuse, which is square root of 6 h bar. So h bar cancels out. So whatever theta is, its cosine is equal to 2 over square root of 6 h bar. So any vector on this cone of uncertainty, okay, you have to think of this in 3 dimensions. Any vector in this cone of uncertainty will have, that has a component of 2 h bar would be describing that particle. So you don't know exactly what the angular momentum of the particle is. You just know what the magnitude is, and you know what the z component is, what the component is along the z-axis. So we say that your angular momentum vector is precessing about the z-axis. So the term for that is precession. So you say your angular momentum vector is precessing about the z-axis at this particular angle theta. Okay? What about L equals 1 and M equals plus 1? I'll have you do that as homework. Okay? And let me just show you a better picture of that vector. Here's you can go to this website at wolfram.com. If you want to see documents on this website, a lot of the documents on this website will require you to install a plugin called there's a link there. It will tell you. It's called the CDF plugin, computable document format. So what is this? This is for J is like L. Okay, so J equals 1. So think of J here as L. So L times L plus 1 h bar. That's the magnitude of your angular momentum vector. Okay, so that's the length of this vector. And that's your magnitude. Square root of 2 h bar. When L equals 1, so square root of 1 times 1 plus 1 h bar. That's square root of 2 h bar. That's the magnitude of that vector. What's the z component? That's gonna be m equals that's m equals -1, m equals 0, m equals plus 1. Okay. It didn't update last time. All right. So here you have, okay, this is h bar and that's 2 h bar. Okay. The length of this is square root of 2 h bar. All right, so it could be anywhere on this cone. That vector can be anywhere on that cone, because all of these vectors that are on this cone will have a component of 2h bar. So what I've done here is I picked j equals 1 and m equals 1. Okay, this thing uses j as a more generic term for the more generic quantum number symbol for angular momentum. Okay. And what if I do m equals 0? The z component is 0. And so again, the length here is square root of 2h bar, and the component is 0. And what happens if I do m equals -1? It's going to be a vector pointing downward. Okay, anywhere along this cone, it could be pointing here, it could be pointing there. The magnitude of that vector, the length of that vector is square root of 2h bar. And the component along the z-axis is -h bar. I'm sorry, that was -h bar. I made a mistake earlier. It's not 2h bar, it's up here. 1h bar. mh bar. mh bar, which is 1h bar, not 2h bar. We have m equals 1. Okay. So m equals 1, and then m equals -1 down here. So here, mh bar equals -h bar. You can change your j to 2. You can change your j to 2. Okay. So j equals -2, -1, 0, +1, +2. Okay? So you can see your z component here is 2h bar, your z component here is h bar, z component here is 0, z component here is -1h bar, and the z component here is -2h bar. All of these vectors have the same magnitude. The magnitude is square root of 6h bar. Okay, looks like I just gave you the answer to the homework earlier. If j equals 1. All right, so. Huh? Oh, yeah, there's the precession. So, I didn't realize it's there. So we say your vector is precessing about the z-axis. So you don't know where it's really pointing. It could be anywhere along that, anywhere in that cone of uncertainty, we say. So what we have is a cone of uncertainty for our angular momentum vector. Right? So new word for today, precession. P-R-E-C-E-S-S-I-O-N.